Hello, everyone. Thank you very much for tuning in today. My name is Elliot Foley, and I'm a PhD student at James Cook University. Today, I'll be taking you through the product of a multidisciplinary and multi-institutional research collaboration, looking at the Mesozoic tectonic history of Eastern Gondwana and reconstructing it from the rock record of Eastern Australia. So jumping straight into the background to this project, we know, for example, that much of the Phanerozoic, particularly from the Cambrian to the late Triassic period in Eastern Gondwana and in larger Eastern Australia, was dominated by contractional processes preserved now in the exemplary rock record of the Tasmanids. So the main constituents of the Tasmanids are shown in the map on the right, and you can see also the geological timescale on the far right, calibrated with the contractional and extensional periods experienced by the Eastern Gondwana margin throughout the Phanerozoic. So you can see indeed that this period from the Cambrian to the late Triassic is dominated by contractional events with some more brief interludes of extensional processes. Conversely, you can see that the period from the mid-Cretaceous, approximately 95 million years ago onwards, is dominated by extension, leading to the fragmentation of Gondwana and the opening of the Tasman and Coral Sea basins, and also the rifting of Zealandia away from Australia. However, we are unsure what tectonic processes were active in this period in the middle from the late Triassic to the mid-Cretaceous. Very little is known about the tectonics of this period, and the reason that this is important is because during this time, the sedimentary fill of the Great Australian Superbasin was deposited. So two principal hypotheses have been debated over the years in the literature about what the tectonic setting of Eastern Australia was like during this period. So the first indicates a rift-related silicic large igneous province was in place from approximately 135 to 95 million years ago. So a very much Cretaceous feature precipitated by rifting occurring in the late Jurassic. The second favors a long-lived continental magmatic arc hypothesis, which is essentially a continuation of the convergent margin processes exhibited by the New England origin, which finished about 220 million years ago. So the reason this has been debated so much over the years and has never been conclusively resolved is because there is a complete dearth of Jurassic and early Cretaceous igneous and metamorphic rocks exposed on shore, which would give a better indication of, other than the Whitsunday igneous province, which would give a better indication of what the tectonics might have been like. So instead, to resolve this issue, we use the detrital zircon record of the Great Australian Superbasin. So an important economic driver of this project is not only elucidate the tectonics from an academic standpoint, but also to determine the timing of the sediment fill and the provenance of the sediment fill in the Superbasin, many of the units of which now hold most of Australia's groundwater, coal and natural gas resources. So how do we elucidate the tectonic setting from just the detrital record? The key criteria are the provenance sources, the uranium-lead detrital zircon spectra, and the hafnium isotopic characteristics of the detrital zircons. So for an arc setting, you would expect an easterly provenance consistent with an eastern magmatic arc, dominated by very young grains, so very much a skewed young uranium-lead detrital zircon spectra. And as you expect this to be a continuation in the New England origin convergent margin processes, you would expect the hafnium values of the period throughout the Mesozoic to be consistent with those already recorded in the New England origin. That is juvenile sourced, juvenile mantle-derived magmas, i.e. returning a strong positive epsilon hafnium signature uniformly and consistently throughout the Mesozoic. Conversely, with the silicic large igneous provenance hypothesis, you would expect a much more varied provenance with a much greater contribution of older cratonic sources, as indicated by the older uranium-lead detrital zircon spectra. Likewise, you would expect quite a paucity of Jurassic grains during this time, as the silicic large igneous province is very much a Cretaceous feature, is hypothesized to be a Cretaceous feature. So you would expect the Mesozoic record to be quite disjointed and episodic. Also, the hafnium profile of the silicic large igneous province will be very much a more variable and more negative signature, gradually becoming more positive towards the end of the Jurassic and into the early Cretaceous as rifting advanced and you have more upwelling of mantle-derived materials, indicating a more juvenile positive epsilon hafnium signature. So moving into our results, We analyzed almost 7,000 zircons from across the breadth and temporal extent of the superbasin, and we returned a significant Paleozoic and even more significantly, 18% Jurassic Cretaceous population. And as there is almost no Jurassic Cretaceous igneous or metamorphic sources for these zircons known in mainland Eastern Australia, we have to ask the question about where these came from. So also, once the Detrell zircon record is broken out in terms of the various strata from Triassic age, Jurassic, early and late Cretaceous ages, you see that there is a very continuous record of Mesozoic magmatism across the superbasin, which is far more consistent with the magmatic arc hypothesis than the silicic large igneous province hypothesis. Note as well that there are also key magmatic pulses at approximately 160, 140, and 100 million years ago in figure B. So if you look at figure C, you actually can see that there's a very relatively short lag time between the crystallization age of the zircon and the depositional age of the unit from which the sample was analyzed. So this is very much consistent with convergent margin settings, so settings such as four-arc basins, back-arc basins, and foreland basins. So convergent margin settings overall, again, very consistent with the magmatic arc hypothesis rather than the rift-related silicic large igneous province. So moving into our hafnium isotopic analysis, the vast majority of our hafnium signature were between +8 and +12, so very uniform, very consistent, very strongly positive, as shown by the histogram and the pie chart on the bottom of the slide. So as you can see from the upper slide, this trend persists throughout the Mesozoic and is almost identical to the hafnium signature previously published for the New England origin. So again, very, very convincing evidence in support of the magmatic arc hypothesis, especially when you can see overall that throughout the Tasmanides, it appears that contractional periods are associated with more negative or variable hafnium isotopic values, and periods of interpreted extension, such as with arc retreat during the Mesozoic, would be associated more with juvenile source magmas upwelling and giving you that strong positive epsilon hafnium signature. So overall, the hafnium and uranium lead data suggests that the eastern margin of Gondwana from the Carboniferous through to the mid-Cretaceous was dominated by a magmatic arc system, which began retreating sometime between the late Triassic and the mid-Cretaceous. So this is very much not inconsistent with the silicic large igneous province hypothesis, which, as mentioned previously, would be expected to generate a much more negative and a much more variable epsilon hafnium signature throughout the Mesozoic, due to the fact that large amounts of crust would have to be melted and recycled due to the interplate nature of the silicic large igneous province. So this kind of rifting and melting of older crust would typically generate more negative signatures. So as the uranium, lead, and hafnium data both are commensurate with a magmatic arc hypothesis, we reconstructed the tectonic history of Eastern Gondwana, as shown in this figure on the right. So, and we used the detrital zircon record from the Great Australian Superbasin, particularly everything younger than approximately the late Carboniferous, so consistent with the arc that we have data for, and consistent with the fact that we know where the edge of the continental crust was at 305 million years due to the presence of subduction complex. So everything eastward of the subduction complex, which is shown in the figure, in the first panel of the figure on the right, everything to the east of this was generated after 305 and between 305 and 95 million years ago. So using the detrital zircon record of the superbasin, we were able to elucidate and estimate what the potential crustal growth rates during the Mesozoic period might have been for Eastern Gondwana. So we found rates between 55 and approximately 80 kilometers cubed per kilometer per million year. These are consistent with accretionary margins worldwide, and in particular with continental magmatic arc systems, such as those of the North American Cordillera, which was contemporaneous at this time, contemporaneous with the Eastern Gondwana margin. But in contrast with the North American Cordillera, the Eastern Gondwana margin, this new juvenile new crust is preserved as sedimentary basin infill and now submerged attenuated crustal ribbons due to the extensional arc retreat nature of the system, rather than the dramatic topography and uplift generated in the North American Cordillera.